Continue. So now we're going to talk about regularized fitting. Again, this is a topic that you might be familiar with from APS 1070, but now we're going to get a bit deeper into this topic. So with regularized fitting, essentially we use some penalty in the objective function and do not fit the model using ordinary squares anymore. We fit it using some regularized fitting procedure. So that gives us either ridge regression or lasso regression. So in ridge regression, we use L2 norm or L2 penalty, and in lasso, we use L1 norm. So let's start with ridge regression. So in ridge regression, the objective function that we want to minimize is not RSS anymore. RSS was residual sum of squares. Now the objective function is RSS plus sum of plus lambda times sum of beta j squared for all the predictors. So this is what we try to minimize. So minimizing RSS was what we had before, I guess in week 2 of the course, when we pick the slope and intercept such that this thing becomes as small as possible. Now we want to make this whole function as small as possible. Therefore, we get some sort of trade-off between fitness and size of the coefficients. Because the second part of the objective function will be minimized where all these betas are 0. And RSS is minimized when the fitness is as good as possible based on historical data. When we have both of them, we get some sort of trade-off. And this lambda in here is some tuning parameter that kind of indicates our preference for fitness versus our preference for sparsity. When many of these coefficients are shrunken to 0, we get a sparse model. So we need to tune the value of lambda using cross-validation. So that's why cross-validation is such an important and versatile method in statistical learning. Pretty much whenever we deal with making a choice about some parameter, the answer is cross-validation. We see it again and again in this course. So this function gives us ridge regression, and here is an example. So here on the x-axis, we have values of lambda. The x-axis is in logarithmic scale. So lambda can be 0. If lambda is 0, we have ordinary squares, the same system for estimating parameters. There's no regularized fitting in here, because if lambda is 0, the objective function will be RSS. But when there are higher values of lambda, there's higher preference for sparsity compared to fitness. So we don't mind sacrificing fitness for the sake of getting a sparser and simpler model. So what happens here is that these are the standardized coefficients of our predictors. So we had limit, credit rating, whether someone is a student or not, and income. So these are standardized coefficients, meaning that for those columns, we have divided the values by the standard deviation of the column. So that if this one is like 5-digit numbers, and this one is, let's say, 3-digit numbers, and this one is 4-digit numbers, usually they would be somewhat comparable in here. Because as you can see, here the units matter because they are kind of competing with each other. Therefore, they need to be standardized. For regularized fitting, the very first step is to standardize the data. So here, standardization means dividing each column by the standard deviation of that column. We can also normalize them. That means first subtracting the mean from each column and then dividing by standard deviation. Here we have only done standardization, which is only dividing by standard deviation. And as you can see, the standardized coefficients, which are some beta values, for limit, it is some positive value, which means that when someone has higher credit limit, their balance is likely to be higher as well. Same for rating, same for students. Let's say students generally have higher balance, but income has a negative impact in the presence of the other predictors. When someone has higher income, it is more likely that they have a lower balance. So this is predicting balance using these features. And there are a couple of other features which are going to have non-zero coefficients, as you can see. And with ridge regression, when we include the value when we include this term in the objective function with a non-zero value of lambda, we move from a dense model in the left to a sparse model on the right. So to the right we have sparsity or simplicity. To the left we have complexity. So this is the high complexity region. This is the low complexity region. And the way that we can use this plot, this is essentially representing a large number of models. Maybe if we tried every single value of lambda between 0 and 1000, this is 1001 models. So one model is ordinary squares which is this. Ordinary squares is the model that, for which limit, this was supposed to be here. So ordinary squares is the model for which coefficient of limit is this much, coefficient of rating is this much, coefficient of student is this much, and coefficient of income is this much. There are also these many non-zero coefficients for other things whose effect size is relatively small, but they are still in the model. That's why ordinary squares gives us a dense model, and if you want to interpret it, it's difficult. It's not just about income, student rating, and limit. If you want to explain why someone's credit card balance is 200, we cannot provide an explanation using these 4 variables. We need to also mention everything else in the data set because they have non-zero coefficients. But with regularized fitting, we have, for example, a different model based on some value of lambda. So let's say this is where lambda is 80. If we pick lambda to be 80 and estimate the parameters using RSS plus 80 times sum of squares of betas, these are the coefficients that we would get. Coefficient of limit will be smaller, coefficient of rating will be smaller, coefficient of student will be smaller, and coefficient of income will be smaller. So this is how we are essentially, we are reducing the variance of the model. So on the bias-variance trade-off, this model might be better than ordinary squares. But this is just speculation, and in order to actually find the best ridge regression model over values of lambda, we need to tune lambda using cross-validation, meaning that we pick a value of lambda, we fit a model with this objective function, and then we use it in a sort of a cross-validation process to measure its error. So when we measure its error, the MSE, cross-validation MSE, when let's say lambda is 0.1, the cross-validation MSE is here. For ordinary squares, the cross-validation MSE is here. And then we try different values of lambda. This can be, again, on a logarithmic scale. So this thing can be maybe 1,000. Maybe this is 100. And then we may get a plot like this. Again, in this plot, ideally, this is where we want to be. And in the example I provided, this could be lambda equal to 80. So this is the tuned value for lambda. Now that we have lambda, we go back and fit the ridge regression model on all the training data set. Because this is from cross-validation, right? And the models are based on some fraction of the accessible data, because some other fraction was used as validation in different splits. So this is how the value of lambda is chosen. And in this model, you can see that the coefficients are shrunken towards 0, but they are not exactly 0. Also, these other ones, it would have been ideal if these other ones would become exactly 0, so that it does some sort of model selection for us. But these ones are not 0, are very close to 0, so we can kind of disregard them. And in this model, we can provide an explanation of why someone's balance is, let's say, $2,000 by just using these 4 predictors. If we want a model even simpler than this, we can try a larger value of lambda. So if we try this value of lambda like 100, income is going to have a coefficient very close to 0, so we can disregard it, and this gives us a different regression function with 3 predictors. And yeah, eventually, to the right of this, when everything becomes almost 0, we have a model very similar to M0, a model with no predictor. But it wouldn't be exactly M0 because they are still in the model, they just have some tiny effect as if they were not in the model. So this is ridge regression. Any questions? No? So in ridge regression, this is L2 norm because when we have a vector beta with these coefficients, let's say beta 1, beta 2, all the way to beta sub p, when we have this vector, the L2 norm of beta is represented like this. This is L2 norm, which is a measure of kind of length of this vector. So it equals the square root of this. As this is called L2 norm or L2 distance, this is essentially an L2 penalty in the objective function. All right, so this was ridge regression. And in terms of bias-variance trade-off, it may give us something like this. If we want to also separate out the effect of bias and variance, the components of error, so this one is, for example, MSE. Variance, when we increase values of lambda, variance actually decreases because we're getting closer and closer to a sparse model, to a model that has only bias. So this can be the irreducible error epsilon. So variance would be, I guess, something like this. And bias squared well, interestingly, up to this point, which is the suitable value of lambda, bias doesn't increase that much. So it's kind of, maybe it increases a little bit so far up to here, but it is worth it because for this much increase in bias, we're decreasing variance by quite a lot. But at some point, bias becomes just too large. That's why we don't want the model to become too sparse for the sake of prediction. So when we move to the right, in here, both prediction becomes better and interpretability becomes better. This is very unusual based on what we know in machine learning, that usually when we want to make something more accurate, it becomes less interpretable. But with ridge regression, at least for the first half of the story in here, the model is becoming more accurate and it's becoming more interpretable as well. So this was ridge regression, and lasso regression is a very similar idea, except that it uses L1 norm. Before discussing lasso, do you have any questions? No? All right. So back to here. We are discussing regularized fitting. We covered ridge regression. Now we're going to talk about lasso regression, where the penalty function is just a bit different. It uses L1 norm, which is the sum of absolute values. So ridge regression is an idea from maybe 50 years ago. Lasso regression is an idea from maybe 20 years ago. So with lasso regression, what we try to minimize is again RSS, and we add some penalty, but the penalty involves L1 norm, which is absolute value of beta sub j over the p predictors. So again, this lambda in here is the tuning parameter that is tuned using cross-validation. So in terms of the coefficients, with the same data set, again, if we have standardized coefficients on the y-axis and value of lambda on the x-axis, if this is 0, the behavior that is kind of expected is that, again, these are maybe the coefficients from ordinary least squares. So this is when lambda is 0, we have ordinary least squares. And there are a couple of non-zero coefficients here as well, actually many of them. It's really unusual in ordinary least squares that we exactly get beta equals 0. So actually all of them are non-zero. But these are not that important because the effect sizes are small. So they are not, they are adding complication to the model without really mattering that much for prediction and with, kind of preventing interpretability. So we want to kind of get rid of these. So with lasso regression, so let's say the limit changes like this. So this is the coefficient for limit, for credit card limit. For rating, we may expect a behavior like this. Initially it increases, then it decreases. So this one is rating, credit card rating, credit rating, right? Credit score. Student, something like this. And for income, and all these other ones, they shrunk to exactly 0 very quickly. We kind of get rid of them very exactly and very efficiently. That's the advantage of lasso regression. So with lasso regression, one main difference is that this line in here is exactly 0. So what this means is that maybe let's say here it's 1,000, maybe here it's 100. All right. So again, in terms of using this model, this vertical line here represents ordinary least squares, the coefficients we would get if lambda is 0. If lambda is 0, the objective function is just RSS. So we get all these non-zero coefficients, including these ones, which are not helpful. So then when we try a larger value of lambda, you can see that these coefficients change. The coefficient for limit decreases, then coefficient for rating actually doesn't have a monotone behavior. Initially it increases. Then it starts decreasing, student decreases monotonically, and income, which was negative, again gets kind of shrunken towards 0. So all of them eventually become 0. This means that if we, try some large value of lambda, maybe 5,000, maybe this is where lambda is 5,000, then the model becomes M0 exactly, becomes the model with no predictors, the model that has low variance, right, and high bias. But here we have high variance, and there's a way to get rid of some of that variance without sacrificing too much on the bias. Again, in terms of bias-variance trade-off, if these are components of error, This can be maybe 5,000, just like the example there. This is 0. So this is the suitable value of lambda. It's not 80 anymore, despite the fact that this is the same data set. Lambda in here means something else, because we multiply lambda to absolute values of beta, not to their squares, right? So in here, lambda can be some larger value, so maybe it's 200. So when lambda is 200, MSE is at its minimum, and that minimum is still, something above irreducible error. Irreducible error is kind of our lower bound. There's no way that we can achieve this. Again, variance works like this, I guess. And at the beginning, bias doesn't increase that much. That's the whole magic of regularized fitting. It starts increasing, but it is worth it up to here, and then it kind of increases too much, and the model becomes too sparse. So this is the suitable value for lambda, which we get from cross-validation, right? So this is MSE from cross-validation. So this is called lasso regression, and this thing is L1 penalty. This is because when we have a vector like this, the L1 norm of the vector, so beta is a vector, the L1 norm is represented like this, which is just sum of beta 1, absolute value of beta 2, all the way to absolute value of beta p. So again, in here, what we try to minimize is fitness, achieving fitness and achieving sparsity. So if we pick a model that has good fitness but high values of beta, it will be penalized because of this, and the objective function will not be at its minimum. So I guess this pretty much covers it. So just to give you an example, maybe in here, if we try this value of 200, which we got from cross-validation, it's going to give us 3 non-zero coefficients. So non-zero coefficient for student, for rating and limit, and 0 coefficient for everything else. This is essentially saying that lasso is doing model selection for us. So in here, it's going to give us, it is going to exactly give us some M3. This is some M3 because the coefficients of everything else is 0, only there's non-zero coefficient for student, rating, and limit. So this is some M3 that has rating, student, and limit. So with lasso, essentially, we're fitting model to historical data and at the same time doing model selection automatically. This is the advantage of regularized fitting. It takes care of 2 purposes for us at the same time. Any questions? All right, so this method is, these methods are, as I said, from decades ago, but at that time they were not that popular because minimizing this was difficult computationally. But because of the advances in convex optimization, these are objective functions that are solvable for us even if p is a very large number. And because of that, we can use lasso and ridge regression on data sets where p is large. Even if it is larger than n, these 2 regression models work. And that's ideal for machine learning in situations when we have short and wide data sets where p is larger than n. So when p is larger than n, ordinary least squares fails, ridge works, and lasso works as well. But between ridge and lasso, typically ridge has higher predictive accuracy. Lasso has some advantages in terms of interpretability because it gives us a model exactly with 3 predictors. So if we want to explain it to, let's say, someone from medical sciences or some practitioner, we would tell them that all you need to do is having 3 measurements from your patients. You need to measure their, blood sugar and 2 other things, and then our model predicts the outcome of the treatment for that patient with just 3 medical variables, 3 medical measurements. Ridge, on the other hand, has better accuracy usually because typically the data generation process is not sparse. So ridge is going to give us a model that is kind of regularized, but it is not exactly sparse. So it is more flexible because even when it shrunkens the coefficients, they don't become exactly 0. Therefore, they will still have the chance to make an impact on the predictions, and therefore the predictions will be better. So, but you might be wondering why in lasso regression we get exactly 0, and in ridge regression we don't get 0. So let me give you an example with 2 feature spaces. So let's say we have 2 variables, x1 and x2. Sorry, actually the coefficients of x1 and x2. So this is possible values for beta 1 and possible values for beta 2. So with ridge regression, what happens is that essentially we have this L2 norm, and the L2 norm is equivalent to having some sort of restriction on the kind of budget we have for the coefficients. That restriction is in form of a circle. This is because this thing under the square root gives us a circle, right, in 2 dimensions. But with lasso, we have sort of a diamond shape. So we have something like this. We have restriction that are kind of, they have sharp edges. And then the estimated vector we get from ordinary squares is here. So ordinary square says that beta 1 should be this much and beta 2 should be this much. This is what ordinary square says. Also in here, it says it should be beta 1 this much, beta 2 this much. But with regularized fitting, we're kind of trying to achieve a trade-off between sparsity and fitness. Therefore, if this is the point where RSS is at its minimum, this contour line in here is where RSS is, has certain difference from its minimum. So maybe here RSS is 10, here RSS is 100. Here RSS is 1000. So when we try to kind of look at these contour lines of RSS, the first point where these contour lines overlap with the restriction we have will be somewhere like here, where both beta 1 and beta 2 are non-zero. It's very unusual that these kind of shapes, these contour lines, happen to intersect exactly on this point or exactly on this point. So they're going to intersect somewhere like here, where none of these 2 betas are 0. But when our restriction has like sharp corners, we get the same contour lines, but these contour lines are going to intersect here in one of the sharp edges. And in this sharp edge, beta 1 is 0. Therefore, it shrinks beta 1 to exactly 0. So this is the difference between using L1 penalty and L2 penalty, and the fact that lasso exactly does variable selection, model selection for us, but ridge only regularized the coefficients. So that's the main difference. Yeah?
Can you repeat one more time what the circle and the line was?
The circle is this. If our budget is, let's say, some S, this circle is beta 1 squared plus beta 2 squared equals S. Or let me write it as budget. So this objective function in here, we can rewrite it using Lagrange coefficients, and essentially this thing becomes a constraint for the model. The constraint is that this sum should be less than some budget. And the same thing is true for this model. We can rewrite it such that this thing becomes a constraint, and that constraint in here would be absolute value of beta 1 plus absolute value of beta 2 is less than, inside it it's less than the budget. On the kind of the border, it's equal to the budget. But actually the coefficient, the constraint is less than or equal to the budget inside this diamond. And inside this circle, of course, the sum of squares of this will be less than the budget. So the first point where ridge is going to match with kind of that trade-off will be some random point on this circle. But for the diamond, it has corners. So in optimization, you know that the solution to a linear programming model has to be in one of the corners, right? Therefore, these contour lines are going to intersect with one of the corners first. Yeah? The contour line. So this point in here is minimum, is some beta that we get from ordinary squares. So this point minimizes RSS. This one, this is the collection of points that do not minimize RSS, but give us some trade-off between sparsity and RSS, such that RSS in here is a certain value. Maybe it's 100. For all of these, this is the collection of possible values for beta 1 and beta 2, such that RSS becomes 100, because you can have a mix of them. This contour line is where RSS is maybe 1000. Eventually, we need the intersection of some budget for the sum of squares of the coefficients and a contour line of RSS.
So if I understand that the contour line has equal lambda, that's right?
The contour lines have equal lambda. Yeah, but only one point in the contour line is the minimum of this, because there's difference between this point and this point for that objective function. In both of them, RSS is the same, but in one of them, this sum of squared is this much. In the other one, the sum of squared kind of matches with this circle. So we can also have contours for the budget, Essentially, we have, contours of some ellipse shape and contours of a circle, and their intersection is unlikely to be exactly on one of these vertical or horizontal axes. But here we have contours of a diamond, and some ellipse shape, and their intersection will certainly be at one of the corners.
So if we adjust lambda, it will adjust the shape of the circle or the shape of the square.
When we change lambda, we are changing this, changing the budget. Yeah. So budget is some function of lambda, because we get it when we rewrite this that has lambda as a coefficient. Any other questions? Again, these ones are available on the lecture slides and in the textbook. All right, let's take another quick break, and the very last topic we're going to discuss is going to be dimensionality reduction for getting a sparse model.